live broadcast now. Okay, I think we are live. So welcome everyone back to our second session of the day. We have a pleasure to welcome David Tong, who is also here in Durham. So David, without further delay, pun intended, why don't you take it away?
Thanks, Tim. Your introductory skills have improved no end in the last 2 days. Thank you. Do you know, for the first time in 18 months, I get to genuinely say thank you for someone's hospitality. So thank you very much to Tin and Nabil and all the other organizers. I made the slightly unusual move of attending an online conference in person. So I've had a lot of fun here in Durham, catching up with some friends and chatting physics. We didn't figure out a way to speak to a live audience though, so everybody's next door and I'm sort of locked in a room on my own. But I do have this wonderful thing behind me where I can do all sorts of fun games. If anybody begins to get an epileptic fit in the middle of this talk, then let me know and I'll turn this off. Let me. Nope, not that one. Let me just share my screen. And why isn't that working? All right. And sorry, I'll be right with you. I think after 18 months I'd have figured this out, but somehow the share screen thing isn't coming up. All right, here we go. Very good. Is it working? People see my screen, maybe even twice. Very good. Okay, so I'm going to tell you about some work I've been doing over the past year. To begin with Shlomo Razamat, and then there was another paper I wrote on my own earlier this year. And it's about a very simple question in quantum field theory, which goes by the name of symmetric mass generation. And the question is the following. It's you take a bunch of massless fermions and you give them a mass. And the question we want to ask is simply what symmetries get broken when fermions get a mass. So it's really sort of a zeroth order question in quantum field theory. To set the scene, let me just tell you things that you know already. Here's the simplest example. In 4 dimensions, if you have a massless Dirac fermion, it splits up into 2 Weyl fermions, and there are 2 U1 symmetries which rotate the left-handed and right-handed fermion independently. When you give it a mass, one of those U1 symmetries is broken. So the diagonal U1 symmetry is preserved in that case, and the axial or chiral symmetry that rotates the left-handed and right-handed fermions in opposite directions is broken by the mass term. So it's something very familiar. Something else very familiar, take the theory that describes our world. This, of course, is the standard model. The standard model is a chiral gauge theory, which means that there's no way to write down bare mass terms in the Lagrangian. And the way all fermions, fundamental fermions, get a bare mass in our world is through coupling to the Higgs boson. And they get a mass when the Higgs boson gets an expectation value, but in getting an expectation value, it also breaks the gauge group, it breaks SU2 times U1 down to electromagnetism. And the question we want to ask is this necessary, or is this just an artifact of weak coupling physics? In particular, is it, for example, possible that there's some other way that the fermions in the standard model may get a mass that does not break electroweak symmetry? So that's the kind of question that we're going to ask. It's obvious you can't do it through weak coupling. It's obvious that with a weak coupling, the Higgs mechanism is the only way to give fermions a mass in the standard model. But there may be some more interesting, strongly coupled dynamics that allows, say, one generation of fermions to get a mass without breaking electroweak symmetry. So that's the kind of question that we'd like to ask. Slava, your
I'm
camera.
sorry, I don't understand the question, David.
Okay.
Because if there is no weak coupling, then there are no fermions, there are no fundamental fields. So what does it mean that fermions get a mass if it's not a weak coupling?
I'll ask the question more precisely in a few slides' time. So I'll make it clear. But roughly speaking, you start with massless free fermions. You introduce new interactions, and you want to introduce new interactions in such a way that they get a mass preserving some symmetry. But I'll try and make this more precise as the talk goes on.
Okay, thanks.
All right. I should say that this question of symmetric mass generation is something that's really come out of the condensed matter community in recent years, starting with the work of Fitkowski and Kitaev on interacting topological insulators. They were very much interested in certain discrete symmetries which would protect or seemingly protect fermions from getting a mass, things like time reversal in odd dimensions, or some chiral parity transformation that only acts on left movers and not right movers in 2 dimensions. So there's a very interesting story there. In this talk, I'm just going to focus on continuous symmetries, and I'm also just going to focus on 4 dimensions. The papers had examples in 3 dimensions and in 2 dimensions, and did discuss discrete symmetries, the papers that I wrote in the last year, but I'll just focus on continuous symmetries. All right, let me tell you why I care about this. And the motivation comes very much from this very old but very important and still open question of how you put chiral gauge theories on the lattice. So I'll spend maybe 20 minutes just giving a summary of what the Nielsen-Niedermeyer theorem is. This is an obstacle to putting chiral gauge theories on the lattice. Give you some cartoon version of it, and explain why symmetric mass generation may be useful in this context. All right, oh, and by the way, feel free to just jump in and ask questions at any time. I don't think I'll take a break, I'll just keep going, but I'm very happy for people to ask me anything at any time. All right, so this slide is a cartoon proof of the Nielsen-Niedermeyer theorem. So the Nielsen-Niedermeyer theorem, if you've not heard of it, says you cannot put one version of it, you cannot put a single chiral fermion on a lattice, meaning that if you take a theory of a chiral fermion and try to discretize space-time, or in fact even just discretize space, the lattice will rebel and it will not allow you to have just a single chiral fermion. So here's, as I said, a cartoon version of the Nielsen-Niedermeyer theorem, and it's going to be the version of Nielsen-Niedermeyer in 1+1 dimensions. So in 1+1 dimensions, space is just a line. Chirality is very easy in 1+1 dimensions. If you have a massless fermion, it can go at the speed of light in that direction, or it can go at the speed of light in that direction. And so the claim is that you can't put a single, say, right-moving fermion on a lattice in 1+1 dimensions. So let's see how this works. Firstly, it's worth saying there is nothing whatsoever wrong with putting a single right-moving fermion in the continuum. It's just a free quantum field theory. I'm even assured that it's a free quantum field theory that can be defined at the standards of rigor of a mathematician. There's really no issue whatsoever in defining such a theory on the continuum. Here I've written down the dispersion relation, the energy versus momentum relation for a single right-moving fermion. The energy is proportional to the momentum with a plus sign, which means that the energy versus momentum has a positive slope because by Hamilton's equations, the velocity is the derivative of the energy with respect to the momentum, and the velocity of such a particle is always positive. So that's the dispersion relation for a right-moving fermion. I should stress something early on here, is that drawing this picture is working in Dirac's original perspective of what fermions were, which we now know is not quite the right picture, but it's sort of the most useful way for proving this theorem. So you see there are negative energy states and there are positive energy states. And the way to think about this is that all the negative energy states are filled and the positive energy states are unfilled. In particular, that means that if you have a hole, it's an absence of negative momentum, and therefore a hole also has positive momentum. So that's the way to view this. Now, on the left is the picture in the continuum. If you make space discrete, something interesting happens. So I think 0th order fact in any solid state physics course is that if space is discrete, then momentum becomes a periodic variable. The 0th order fact in your first quantum mechanics course is that if space is periodic, momentum is discrete. The Fourier transform of that statement is basically Bloch's theorem that if space is discrete, the momentum is periodic. What that means is, for our chiral fermion, is that the dispersion relation should be, again, a function of energy versus momentum. But momentum, this horizontal axis, is now a circle. Momentum of pi over a is identified with momentum of minus pi over a. This is what our condensed matter friends call the Brillouin zone. And if you want physics to be local, then the energy versus momentum relation should be continuous. So from this picture here in the continuum, you have a problem because momentum pi over a here should be the same as momentum minus pi over a here. And it means that this energy versus momentum relationship, to be continuous, having gone up in the middle, has to come down again and meet well, somewhere, but typically you find that it meets at the edge of the Brillouin zone. So if you just take a Weyl fermion, you do a very naive discretization, you'll find an energy versus momentum relation, which goes as a sine, which of course looks linear near the origin and reproduces the continuum result, but crucially bends over and has another place that it intersects the horizontal momentum axis. So this is the essence of the Nielsen-Ninomiya theorem. What's going on here is you try to put a single right moving fermion on the lattice. That's the modes at the origin. But the lattice rebels, and in rebelling, it generates new low energy states. Those new low energy states have very high momentum. It's momentum close to the lattice cutoff. But nonetheless, they have low energies. And in quantum field theory, it's low energies that we care about, not so much low momenta. Of course, in relativistic theories, low energy and low momenta come together, but on the lattice, they do not, and you get new low energy states. Moreover, those new low energy states are a fermion with the opposite chirality. It's the opposite chirality because here the slope is positive, and here necessarily the slope is negative. So the upshot of the Nielsen-Ninomiya theorem is that if you try to put a chiral fermion on the lattice will rebel and give you another fermion of the opposite chirality. In fact, in higher dimensions, it gives you some number of extra fermions of different chiralities. So you try to put a chiral-like theory on the lattice, and the lattice hands you back a vector-like theory. So I think most people in the audience are probably very familiar with this, but if you're not, these extra fermions are called lattice doublers. They're sometimes called mirror fermions, and I'll use both terminology in this talk. So the Nielsen-Ninomiya theorem here has two parts. It's firstly that you can't put a chiral fermion on the lattice, you get the doublers. Secondly, if you can't try to couple forces to these fermions, at least if you try naively, whatever your original fermion feels, the doublers will also feel. Roughly speaking, because they're coming from the same field. So if you couple this fermionic field to, say, a gauge field, this fermion will experience that force, but this fermion, the doubler, also will, again, meaning that you get a vector-like theory on the lattice, not a chiral theory. So this is the Nielsen-Ninomiya theorem. It dates back to the early 1980s. And the question is, how can we find a way to try and evade this theorem and ultimately, ideally, simulate chiral gauge theories on the lattice? Okay. Any questions about this?
David, can I ask one question about this?
Yeah, sure.
So so does it mean that this theory only apply for like even space-time dimension, where you can define chirality, or is there a version of that in, let's say, odd space-time dimension as well?
Yeah, there's a version in odd space-time dimension to do with time reversal. It's time reversal that stops fermions getting a mass in odd space-time dimension. So again, Dirac fermions come in some number of pairs, so that the full theory is time reversal invariant.
I see. Okay, thank you.
Any other questions?
Just a remark, I'm sure you will say this very soon, but Martin Lucia did construct chiral gauge theories by maneuvering around the theorem and so on. I guess this is what you will get to.
I'm not going to go in the overlap direction actually, but yes, and it's extremely interesting. He did only in the abelian case. He was not able to do it for non-abelian theories. I think Kikukawa has subsequently claimed to make progress in the non-abelian case, but I don't fully understand that. But there certainly is a direction using overlap fermions, which is very interesting. It's not the direction I'm going to go in. But yes.
I mean, there's just a very hard technical problem for non-abelian gauge theories. It's not that Martin Lüscher didn't do non-abelian gauge theories. They actually constructed chiral non-abelian gauge theories to all orders of lattice perturbation theory.
But it's the non-perturbative question.
Yeah, but still, I mean, in the continuum, they are sort of by recipes constructed only at the few loop order, and he constructed them to all orders in perturbation theory on the lattice.
Oh, I see. And you're right. The even perturbative regulators for chiral gauge theories are hard to come by in the continuum. I see. So you're saying he did better on the lattice than we can do in the continuum. That I can believe.
And there's just some very hard problem. I don't understand it, and Martin Lüscher couldn't solve it. So it must indeed be fairly difficult.
It's also worth pointing out, though, that that there are very simple abelian chiral gauge theories in 1+1 dimensions that would be worth simulating. Two fermions, two going that way with charges 3 and 4, two going that way with charges 5 and 0. But this technique of overlap fermions does not allow you to solve them, even very, very simple ones in low dimensions like this. So I agree that I actually think it's very important to have an in-principle proof that it's possible. But it would be nice to actually be able to get to a point where you can simulate strongly coupled physics in chiral gauge theories, and the overlap approach does not seem to get there.
Okay,
Slava, you have your camera on. Does that mean the question is forthcoming? No? Okay, very good. All right. For what comes later, let me just tell you a slightly different avatar of this setup. We won't need it until about an hour's time, I suspect, but it's beautiful story in its own right. So there's another way to see this doubling, and it's an idea that dates back to the anomaly inflow story of Callan and Harvey in the continuum, but the lattice approach was really pioneered by David Kaplan. And the version I'm going to tell you here is due to Shamir. The idea is the following. You start in 1 dimension higher than the theory you care about. So let's say we care about 4-dimensional physics. Let's in fact say we care about the standard model. Instead of looking in 4 dimensions, you look in 5 dimensions, but where the extra dimension is an interval. And you consider massive fermions in 5 dimensions. And because it's an interval, you have to impose certain boundary conditions on the end. And with suitable boundary conditions and suitable tuning of parameters as well, you find that there are gapless modes that are confined on one edge. So these are really just Jakiv-Rebbe zero modes on domain walls, but here a latticized version. And you have left-handed modes on one edge, and you have right-handed modes on the other edge. So again, you see the doublers. The difference is that the doublers are now separated in position space rather than in momentum space, as I showed in the previous slide. That's something that's useful, and we'll return to this briefly at the very end of the talk. All right, so how do we evade the Nielsen-Niedermeyer theorem? And as Uwe Jen said already, there's an extremely interesting story to do with the Ginzburg-Wilson relation for Dirac operator and its solution through overlap fermions. I'm actually going to take a slightly different and, in fact, slightly older approach to this. So we have the original fermions and the doublers, either in momentum space or in an extra dimension. And if we're going to evade the Nielsen-Niedermeyer theorem, as with all no-go theorems in physics, we've got to find a loophole, got to find one of the assumptions of the Nielsen-Niedermeyer theorem, which we can throw away and therefore make progress. And one particularly obvious loophole is the following. The Nielsen-Niemeyer theorem actually relies on weakly coupled physics. In fact, you can see it here. This story that I've told you here, the whole language that I've used in terms of energy versus momentum is not the language of quantum field theory. It's the language of single particle quantum mechanics. As I stressed, it's Dirac's old picture of solving the Dirac equation. The idea is that maybe we could turn on strong coupling effects. This is an idea that dates back to Eichton and Preskill. And we can do the following. We can try and turn on strong coupling effects that firstly act only at the edge of the Brillouin zone, but leave the things at the origin unaffected. That's challenge number one. And challenge number two is to try and turn on strong coupling effects in such a way that the chiral fermions that sit at the edge of the Brillouin zone all get a mass, but they get a mass without breaking the gauge symmetry that you care about. So suppose the gauge symmetry is the standard model. The idea is that all of the standard model fermions sit at the origin. There are doublers of opposite chirality at the edges of the Brillouin zone, but you want to give these doublers a mass that's parametrically larger than, say, 1 TeV, so they just decouple from the physics, and they leave the gauge fields, particularly the electroweak field, unscathed at the TeV scale. So all the physics below the TeV scale can be the physics that we know and love, and in that way we get to simulate the standard model on a computer. That's the idea of Eichton and Preskill. And again, the way it evades the Nielsen-Niemeyer theorem is simply by saying the kind of language that we're using with energy versus momentum in this dispersion relation just is not the appropriate language for strongly coupled quantum field theories. All right, so how does one do it? Well, there's been a lot of work on this. The original idea of Eichton and Preskill was that you gap these fermions by turning on some kind of 4 fermion operator. In fact, what they really had was 4 fermion operators with a bunch of derivatives in here, the idea being that the derivatives mean that the 4 fermion operator is more important at the edge of the Brillouin zone for high momentum than it is at the origin of the Brillouin zone for low momentum. So the idea was that you could add to the lattice action some 4 fermion terms with some appropriate derivatives, and that turning on these 4 fermion terms would just give a mass to all the fermions. Now, if you're used to continuum quantum field theory and not used to physics on the lattice, this clearly isn't going to work. It's clearly not going to work in the continuum because this is an irrelevant operator. You're not going to give masses to fermions by turning on irrelevant operators. But on the lattice, you can do things that you can't do in the continuum. In particular, you can take the coefficient of this irrelevant operator and you can crank it up so it's very, very large at the strong coupling scale. Sorry, very, very large at the UV cutoff at the lattice scale, in which case it's quite possible that there may be this irrelevant operator could play a role on the lattice and give masses to the fermions where the masses themselves will now be at the UV cutoff. I think it's a wonderful idea, and I think it's an idea that is wonderful and presumably should work. Nonetheless, after how long have we got here? 35 years of studying, I think it's fair to say that nobody's made this fly yet. And it's not through want of trying. There's been an awful lot of people that have pushed this work in various directions. There are also papers that claim it works, except none of those papers actually do the simulation and show it. So by success, I think you really have to do a Monte Carlo simulation and show that these things do indeed become gapped. And it's certainly true to say that nobody's achieved that yet, with an honorable exception of recent papers within the last 6 months by Simon Catterall and friends who do something similar, but where it's not quite clear that you have a Lorentz invariant theory and it's not quite clear what happens. But there is some recent promising work in this direction. All right, so this is the idea of Eichton and Preskill. Are there any questions about the general philosophy here?
Is it clear what obstacle there is to why is it so difficult to gap? Is there an anomaly or something?
There's no anomaly, which is important. I think the issue is the following. So firstly, what actually happens if you turn on this this interaction? What happens? Well, either you find that these things get gapped and the symmetry was broken along with it, or you find that these are gapped, but also the original fermions are gapped. You just find phases that you would expect to find. I think what's going on here is the following, that because this is strong coupling physics at the lattice scale, I think you don't get to rely on your Wilsonian intuition for what's important and what's not important. So there's a 4 fermion term that you've turned on, but there's nothing that tells you shouldn't also be turning on the 6 fermion terms or the 8 fermion terms or the 10 fermion terms. And presumably somewhere within this enormous parameter space, you do indeed find the phase where these things are gapped and the ones at the origin are not. But it's just not been found yet. And you don't know how big the parameter space is that you should be searching. So Eric Poppitz and Shang looked at maybe a 6-dimensional parameter space in some 2D theory and failed to find the gapped phase that they were looking for. So I feel it should work, but you can sort of see that it could become very, very challenging. Uwe Jens, yes, please.
Yeah. Wouldn't you think that indeed the anomalies of the original fermions must cancel in order for this to be possible? So
absolutely. In fact, the next slide says this. But of course, Eichten and Preskill did exactly that. They put an anomaly-free theory here and tried to gap anomaly-free fermions. Even then, it's not been, no one's managed to make it work. But yeah, that's exactly where we're going in the next slide. Sorry, Tin, I think you hadn't finished.
I just wanted to say, so you think it's a fine-tuning problem?
I suspect it's a fine-tuning problem. Yes.
This particular phase we're interested in may just be a point in a very large parameter space.
Yeah, that's my feeling. I'm no expert on lattice theories, but that's my feeling. Yeah. All right, so this is the lattice story. All right. And of these 2 challenges, I'm going to discuss both of them in this talk, but I'm only going to declare success for one. So remember, what are the 2 challenges? Somehow you have to cook up interactions that only the doublers feel. And somehow you have to cook up interactions that gap the doublers, preserving the symmetry that naively would be broken because it's a chiral symmetry. So it's the latter of those that I'm going to focus on in this talk. The question is, how do you gap fermions without breaking a chiral symmetry G? As I said at the beginning of the talk, this is known as a symmetric mass generation. And given the problem that's clearly there when attempting to do it on the lattice, the obvious thing to do is just try and find a continuum mechanism that does this. So just try and work within continuum field theory to find a way to give fermions a mass preserving some chiral symmetry. Having achieved that in the continuum, there's a next question, which is whether it's possible to transport that onto the lattice and implement it in that framework. So I'll primarily focus on the continuum, but at the end of the talk, we're going to jump back to the lattice and see what the issues are when you try to implement symmetric mass generation there. So that's where we're going. This is Uwe Jens's point. What is the real obstacle towards gapping fermions? You see, weak coupling, it appears that the obstacle is the chirality of the symmetry. In the free fermion case, it's the axial symmetry which gets broken when you give them a mass. In the standard model, it's the fact that the fermions are chiral. Left and right-handed fermions transform differently under the symmetry group G, which means that you can't write down a mass term, and therefore that appears to be the obstacle towards giving these things a mass. But in fact, that's not quite the obstacle. And the true obstacle was mentioned by Uwe Jens earlier and was first pointed out by Toft 40 years ago. And so if you take some global symmetry G, the obstacle towards giving fermions a mass is what's called the Toft anomaly. So for discrete symmetries, this becomes complicated, and there's been a lot of progress in the last 10 years, but here I'll just discuss continuous symmetries. And the Toft anomaly is the familiar triangle diagram where you put a global current on each leg. So again, I think most people in the audience know about Toft anomalies, but let me just say 2 words in case you don't. Anomalies that you probably would have heard of The first one we learn is the ABJ anomaly, also called the chiral anomaly. The ABJ anomaly is where you have one global symmetry and two gauge symmetries. And in that case, it's a statement that what you think of, or what is what is a symmetry of the classical theory, fails to be a symmetry when you quantize and go to the quantum theory. That's not what's going on here. If you have a Toft anomaly for a symmetry, the symmetry is a perfectly good symmetry of the quantum theory. There's a conservation law associated to it. If it's a non-abelian symmetry, all states fall into appropriate multiplets. However, what the Toft anomaly is an obstruction to gauging the symmetry. So if you compute the Toft anomaly for a particular symmetry and it's not zero, it's an obstruction to coupling that symmetry or that current to a gauge field. And for our purposes, the beauty of the Toft anomaly is that it's a way to classify the quantum field theory with a particular symmetry. So in the following sense, you could imagine lots of different quantum field theories that have a particular symmetry G. But associated to each of those quantum field theories is a number. It's the Toft anomaly. And if the Toft anomalies differ between those theories, then there's no way to deform one theory into another theory while preserving the symmetry G. So this is a way to characterize the different theories that have the symmetry G. In particular, the Toft anomaly is invariant under RG flow, assuming the symmetry is unbroken, which means that if you have two theories with the same symmetry G but different Toft anomalies, there's no possible way you can flow from one to the other under RG. All right. As was already mentioned by Uwe Jens, this same story means that if you have a symmetry with a Toft anomaly, there's no possible way that you can give everything a mass preserving the symmetry G. Because if you go to energy scales much lower than that symmetry G, there's nothing there to carry the Toft anomaly. There, the Toft anomaly appears to be zero. So you can only gap fermions if the Toft anomaly vanishes. So this is a wonderful thing. In fact, we all know quantum field theory is hard. I think this is one of the easiest things you can compute in a quantum field theory that gives you the maximum amount of knowledge, given how simple the calculations are. So you go to the UV of a quantum field theory where everything is weakly coupled, you compute the Toft anomaly. If you compute the Toft anomaly for a global continuous symmetry in 4 dimensions and it's non-zero, you know for sure that the theory is massless in the infrared. Because two things can happen. One thing that can happen is the symmetry G is spontaneously broken, in which case there are Goldstone bosons. The other thing that can happen is the symmetry is not spontaneously broken. If the symmetry is not spontaneously broken, there have to be massless modes that saturate the anomaly in the infrared. Those modes have to be fermions as well. So one way or another, you have massless modes, either bosons if the symmetry is broken, or fermions if the symmetry is not. In other dimensions and with discrete symmetries, this story is different. There are many experts in the audience who know that you can also get topological quantum field theories that saturate the anomaly. That's not possible for continuous symmetries in 4D. So for us, the important point here is that, as I said before, you're only going to be able to achieve symmetric mass generation if there's no anomalies under the symmetry that you want to preserve. In particular, I gave you two examples at the beginning. The examples were the free fermion, where you break axial symmetry. You're always going to break axial symmetry if you give mass to a free fermion, because the Toft anomaly, the axial cubed anomaly, is non-zero. But the other one was the standard model. And the Toft anomaly for the group G of the standard model definitely vanishes because we actually gauge it in our world. So there should be no in principle obstacle towards giving one generation of the standard model a mass without breaking electroweak symmetry. All right, so where we're going to go in this talk is to figure out exactly how to do that. All right. Any questions?
Hi, David. Can I ask you a very naive question?
Yeah, please.
You mentioned the Dirac case where you're explicitly breaking the symmetry.
Mm-hmm.
Is there an example? Is there an obvious example with spontaneous breaking?
Yeah, actually, we were mentioning it yesterday at lunch. Just replace the mass with a scalar field.
Yeah, of course.
And then let it condense.
Yeah, Sorry.
Sorry, David, in these attempts with 4 fermion interactions, I mean, was the chiral symmetry preserved, or did they explicitly break it?
Yeah, so the explicit the theory that Eichton Preskill considered was an SU5 gut with 1 generation. So you have 1 fermion in the 10 and 1 in the 5 bar. And they wrote down a 4 fermion term which preserved the SU5. Yes. Yeah. And we'll see examples as we go on through the talk. All right. Any questions? Any more questions? All right, so let me say a bit more precisely what I have in mind, and this hopefully will answer the question that Slava had earlier. You know, there's different ways to phrase this. I could phrase this in terms of a theory with a global symmetry that has no Toft anomaly, or I could then choose to gauge that global symmetry and give myself a chiral gauge theory. Both points of view are useful. Here I'll talk about the gauge theory perspective. As we go on, I'll jump between global and gauge symmetries. The general story doesn't matter if the symmetry group G you want to preserve is gauged or global. But here I'll just, for familiarity, because I think I want to have the standard model in the back of my mind, I'll talk about gauge theory. All right, so I've got some chiral gauge theory coupled to some fermions. I want to give those fermions a mass without breaking the gauge symmetry. Can't just write down a mass term, obviously, because they're chiral, and I can't use a Yukawa term because that would Higgs the gauge symmetry. So what can I do? Here's the basic idea. I need to add some extra degrees of freedom into the game. So I start with my chiral gauge theory, and at a very high energy scale, I'm going to add some extra matter, and that extra matter may or may not be charged under the symmetry G. But if it is charged under the symmetry G, I better make sure it's vector-like, because I want to be able to give it a mass. Or said more precisely, I don't want to change the anomalies of that symmetry G. So this means that I can always go to a limit where this extra stuff just becomes arbitrarily heavy, just decouples from my story, leaving the chiral gauge theory. But what I want to do now is deform the parameters of the theory so that this extra vector-like stuff becomes light, interacts with the chiral gauge theory, the upshot being that everything becomes massive, but the symmetry group G is unbroken. And again, you can think of G as global or gauged. It really doesn't matter for this story. So that's the goal, is to deform in the parameter space of the theory to start with a chiral theory and end up with a vector-like theory. In other words, to find a set of theories that obey the unlikely looking equation at the bottom there, that somehow chiral plus vector should be equal to vector, which seems odd. It seems like chirality should somehow be preserved, that chiral theory plus a vector theory should remain a chiral theory. But we want to find a situation where you end up with something vector-like. But by the way, the theory at the bottom, the schematic equation at the bottom is true simply because the right way to classify anomalies, or symmetries, is through the Toft anomaly. And by definition, a chiral theory has a Toft anomaly, which is 0, just as a vector-like theory. Slava, your microphone is now off, so please.
Yeah, I wanted to make sure I understand. So everything becomes massive, but things were already perhaps massive even before you added this vector-like matter. So I guess you want this final mass scale to become arbitrarily large.
I want it to become arbitrarily large, but let me start from the following setup, which I think might be conceptually easier. I'll just take a bunch of free fermions, but insist that they transform in some chiral way under a global symmetry G. And so now they're clearly massless to begin with. And I can't give them a mass, preserving that chiral symmetry G.
So we can just forget about gauge.
Yeah, in fact, it might be conceptually more useful to forget about the gauge now. So just think of this as a global symmetry G, which is stopping these things very clearly from writing down mass terms.
So the only mass scale then is the mass of this vector-like fermions and perhaps some interactions. I don't know. Okay, fine. Now it's better. Thanks.
Yeah, we'll do some examples. I'm going to walk through 3 examples as we over the next 20 minutes to give you some sense about how this works.
And sorry, David, can I just ask one question?
Yeah.
Is the in the language where you take it in the global symmetries, the 'T' anomaly of each of the clouds is individually 0? Is that what I should imagine?
Yeah, that's exactly right. Yeah.
Thank you.
Yeah. And it might be this cloud here is just empty, that everything got a mass. This could just be, yeah, nothing. Yeah. Any other questions? All right, so I'm going to give you 3 examples, and they're going to sort of be, well, they're all going to have something slightly different to exhibit. So here's the first example. It's a very familiar set of chiral matter. My G is SUN in 4 dimensions. And I'll start with a bunch of massless fermions, and I'll think of G as a global symmetry here. I think that's that's simplest. So I have one fermion that transforms in the symmetric representation of SUN, and I have n+4 fermions that transform in the anti-fundamental. And if you've seen this before, it's almost certainly in the context of a chiral gauge theory, and you've seen it in that context precisely because the Toft anomalies cancel, so there's nothing to prohibit you gauging this symmetry G. But conceptually, we'll just keep G to be a global symmetry for now. The question is, how do I give a mass to all these fermions without breaking G? And it's clear, I can't just write down a quadratic term because there's no way to form a singlet from any 2 fermions in these representations. All right, so that's the challenge. Clearly, I can't write down a mass term. I'm in 4 dimensions in the continuum, so 4 fermion terms are irrelevant. They're certainly not going to do it. So I'm obliged to introduce these extra degrees of freedom. So here's the way it works. At least here's a possible way it works. I have to confess, we're not quite sure if this example flies at the end of the day for a reason I will explain. All right, so we're going to add some extra stuff. And the extra stuff I'm going to add is to see that in addition to this symmetry G, there's clearly another SUN+4 symmetry that rotates all of these fundamental guys. And it commutes with this G. So what I'm going to do is I'm going to add a gauge group for this SUN+4. So I'm going to gauge this SUN+4 symmetry. Now, there are 2 things I need to do before I can do that. If I was to gauge this, this group H, and I'm always going to call H this extra gauge field that I add. If I was just to gauge these, but by the way, all of these boxes are, say, a left-handed Weyl fermion. So if I was just to gauge these, H would be anomalous. And I want to gauge H, so I can't allow for it to be anomalous. So I have to add some extra fermions which are uncharged under G, but are charged under H. So I'm going to add this additional fermion, which is in the anti-symmetric, sort of in the anti-anti-symmetric representation of H, but the 2 antis mean different things. So it's in the anti-symmetric bar representation of H. In addition, I'm going to add some scalars, and the whole point of the scalars is that they Higgs H to make all of these gauge bosons heavy, and this additional fermion heavy, and the scalars heavy, so that all of this new stuff, the gauge bosons for H, the additional fermion, they start off life very, very heavy. None of them are charged under G, so doesn't matter. And now the idea is that I'm going to slowly change the VEV of these scalars. All of this extra stuff comes down and becomes light. At some point, I make the scalars very heavy and they just decouple. And then I'm left with understanding the gauge dynamics of this gauge theory H. So the question is now, as I deform the theory, I end up with a strongly coupled gauge theory for H. And is it possible that that strong coupling gauge dynamics for H ends up gapping all these fermions without breaking the symmetry G? That's the question I want to ask. So just introducing some notation. It's exactly the same as we have before. G is SUN and is the global symmetry I want to preserve. H is SUN+4 and is a new gauge dynamics I've introduced. And here's my collection of fermions. So the ones that I start with are the lambda and the psi's. They're both charged under G. And the extra guy I add is what I've called chi tilde. That's only charged under H. And these two, the psi and the chi tilde, are charged under H. Lambda is just a bystander as far as H is concerned. And so now we have a question to answer. The question is, what is the strong gauge dynamics of this chiral gauge theory, SUn+4 gauge theory? And the answer is, we don't know. I'll tell you what we think we know about it next. Are there any questions about the setup, though, and sort of how the hope is that this might give symmetric mass generation?
Can you go back a slide? So you basically want, I mean, you would expect that this strongly coupled gauge dynamics would force you to have kind of baryons of these barred fermions, right? Which are charged under that.
Yeah, that's not what happens.
It's not what happens.
No, we'll see what happens, but I think that's very unlikely to happen. Yeah.
Okay.
I'll give you the suggestions for what we think would happen with this theory.
Okay.
Slava.
Yeah, I just wanted to make sure this new gauge theory H is also chiral gauge theory, right?
It is in this case, yeah. It won't be in later examples, but in this example it is, yeah.
Mm-hmm. Okay.
Yeah.
So David,
Avner, yeah.
the representation of the scalars that Higgs Hn give mass to chi tilde, or?
Yeah, I don't know what they are, but you can add as many scalars as you like. There's no need to have some minimal amount in this.
Okay, you can do it with the same scalar.
Yeah, you don't have to do it with the same scalar. That's right. But so it's trivial to do. I see what you're worried about. But yeah, I can add I'll take two of these, whatever representations appear in that tensor product, I'll add a scalar for each of them. And there's no need to be cautious about what you add in this case.
Okay.
Other questions? All right, so we've got a question to answer, and it's a hard question because it's a question about strong coupling dynamics of chiral gauge theories. Rather ironically, we can't answer it because the big question we're trying to answer is how you simulate chiral gauge theories on a lattice, and we can't do it. So, if we could answer this question, we might be able to answer the big question that we start with. Nonetheless, I think there are two compelling suggestions for what the dynamics of this gauge theory is. So let me run through the two possible suggestions. The first one is a very old suggestion. It goes back to work of Georgi and Dimopoulos and Rabi and Susskind 40 years ago. And the suggestion is the following, that this H equals SUn+4 chiral gauge theory might confine without breaking its global symmetry group. Now, the global symmetry group for this H chiral gauge theory is precisely this G equals SUn that we're desperate not to break. So this seems like it might be good. However, from the perspective of the H chiral gauge theory, G has an anomaly, has a Toft anomaly. Well, why does it have a Toft anomaly? Well, it has a Toft anomaly because the Toft anomaly of lambda and psi together vanish, but H knows nothing about lambda. Lambda's decoupled. So the gauge dynamics of H has a Toft anomaly for G because it comes just from this psi here. That means that if H does confine without breaking G, it has to do so in such a way that there's a massless composite fermion in the infrared, which is interesting physics. Having massless fermions that are bound states of other fermions is surprising and fairly rare. But these authors pointed out that if you just take the simplest possible fermionic bound state, gauge invariant fermionic bound state, which is two of these psi's and one chi tilde, then you end up with a massless composite fermion, which has precisely the right quantum numbers to saturate the Toft anomaly in the infrared. And the quantum numbers it gives you is the symmetric bar of SUn, which noticeably is the conjugate of the lambda that was the bystander. So if this is the right dynamics, it's a beautiful example where you start with a chiral-like theory, confinement kicks in, confinement binds some of those chiral fermions together, and what you end up with in the infrared is a vector-like theory because you've just got lambda and lambda tilde, which have conjugate quantum numbers under SUn. In which case, it's very easy to get symmetric mass generation. all you do is you go back to your UV theory and you add this 4 fermion term, which sounds very similar to what Eichton and Preskill did, except this is an example of a dangerously irrelevant operator. It looks irrelevant in the UV, but as you flow to the infrared, some strong coupling dynamics kicks in. 3 of these fermions bind together and in the infrared become effectively a single composite. And this 4 fermion term in the infrared just becomes a mass term, but it's a mass term which explicitly preserves G, just as the original 4 fermion term did. So if this is the dynamics, and it's a big if, you have a mechanism that gives you symmetric mass generation through confinement of some extra gauge dynamics that you added. Is the punchline clear up to the question about whether this truly is the right dynamics of this theory?
But can you give us some feeling, so these people who conjectured this particular dynamics for the H gauge group, how did they come up with this proposal? Why does this sound particularly natural? And I have very little intuition. What would be the alternative scenarios which don't look as reasonable as this one?
The reason it's natural is I think really its simplicity. This is the simplest gauge invariant object you can write down. And there's a U1 as well, which has a Toft anomaly, which I've neglected to mention here. And it turns out that the simplest confined object you can write down has the right quantum numbers under the SUN global symmetry and the U1 global symmetry to saturate all the Toft anomalies. So it looks like, something special has happened. That's a rare property of strongly interacting quantum field theories. So it's really just simplicity. And I don't think we have any better argument than that. There are other arguments in the literature, but I'm going to debunk them in a couple of slides. So I think it's just simplicity.
But so if we were to take the alternative assumption that G actually gets broken and we would try to saturate the Toft anomaly with Goldstone bosons, then it just looks much more complicated. What did they try to do this?
Yeah, so I'll give you that option as number 2.
Work out as nicely.
Yeah.
Ah, okay.
No, there is a fairly simple proposal for that direction as well. Yeah.
Okay.
Durham room 2 had their mic off, but okay, now it's gone off. All right. So here's option 2. Well, option 2, rather surprisingly, came up only this year. And people have known that it's possible to confine and break the chiral symmetry G, but I think this is the most compelling suggestion along those lines. What they did was the following. They looked at the supersymmetric version of this chiral gauge theory. Now, it turns out the supersymmetric version of this chiral gauge theory has one of those runaway potentials which pushes the SUSY vacuum off to infinity. But they figured out how one could, I'm in the middle of a talk. Can you come back later?
Yeah.
Thanks, mate. It turns out that adding the supersymmetry breaking deformation lifts the potential and gives you some supersymmetry breaking vacuum at some finite place in moduli space. And they argued that, well, they looked at that vacuum. They saw that the global symmetry G, which was SUN, is broken down to some symplectic group. And they argued that maybe this is the right dynamics of the non-supersymmetric theory as well. In other words, if you take the supersymmetric theory and you softly break supersymmetry, this is the chiral symmetry breaking. That's just a true statement. They then suggested that maybe as you take the supersymmetry breaking large, this remains the phase that the theory lives in. There's no evidence for that whatsoever. It could easily go through a phase transition. But they just offered this, I think, as actually, they wanted to make stronger arguments that this was the right dynamics. But I don't believe the stronger arguments, but I do think it's a nice proposal for what happens. If this happens, this simply is not a way that you can give symmetric mass generation, because the dynamics now breaks the chiral symmetry G. The whole point was to find a way that you preserve the chiral symmetry G. So we don't know what happens at the moment. It could be option 1, it could be option 2. But it gives you some idea of the pitfalls involved. So the takeaway message from this part of the talk is that there's a close connection between 2 different phenomena. The phenomenon of symmetric mass generation, where you give chiral fermions a mass without breaking the chiral symmetry, and the phenomenon of confinement without chiral symmetry breaking, where confinement without chiral symmetry breaking is a rare but not unheard of phenomenon in certain non-abelian gauge theories in 4 dimensions. All right. Any questions about this?
Do you know of any example where it is without a doubt the confinement without chiral symmetry breaking happens?
Yeah, I'm going to get to them in the next example.
There is, okay.
Even if it is not what happens, you can add more fields, more scalars, and just find a way to take this symmetric chiral theory to this composite fermion. So for symmetric mass generation, you can still do it, even if it doesn't happen in the usual RG flow. You can add more fields and make it happen.
I think I understand, Avner. You're saying that option 1 is clearly a plausible endpoint for the RG flow, and option 2 is a plausible endpoint for the RG flow, and it's a question of messy dynamics which this particular theory chooses, and that one could change the theory in some way just by adding some scalar fields and maybe therefore change the relative energy levels of these two.
Yeah, and we know how to do it.
That's right, but we've got no idea about how one pushes it in one direction rather than the other. And what we really want here is a definite way, finding a genuine path through field space that achieves symmetric mass generation, rather than just saying, it's plausible, but we don't really know.
No, we know how to add more fields to make it happen. How
do you know?
We wrote it in a paper.
Oh, I see. Sorry, no, you're absolutely right. I did write a paper on this. Yes, sorry, there is a way to add a scalar field and push you in one direction. Yeah, thank you. I'd forgotten about that.
Can I make a follow-up question? So yeah, that was indeed what I was thinking, but naively, there's not many things you can, because you're in the UV, you're in the weakly coupled phase, and then naive scaling in the infrared, relevant and irrelevant operator in the infrared would restrict what you can put, which could plausibly be important. So you're saying there is something that
there is. Yeah, and I've tried to. It gets a little bit complicated and it takes us on a tangent that I'd sort of rather not go down. So maybe we can just chat later, Tin, if that's okay. I think it would muddy the waters more than clarify the points I'd prefer to make. Is that all right? All right. Let me just make a small aside. Yeah, sorry.
Can I ask another thing? Sorry.
Yeah.
Wasn't this expected in the sense that if you had written it without chiral symmetry breaking on the other side, you would have had mass related to confinement? That's
here.
In the in the last slide. Well, yeah, here as well, but in the last slide, you have symmetric mass generation is the same as confinement without chiral symmetry breaking, right?
Yeah, but there's a little twist, because confinement without chiral symmetry breaking always gives you massless fermions, because the Toft anomalies have to cancel. But so the very small twist, and I agree it's a small twist, is that it then allows you to pair those massless fermions with something else in gap. Yeah.
I see.
Let me just make an aside. People have been studying this particular chiral gauge theory for 40 years, and I think our ignorance has increased quite dramatically in the past 12 months, in the sense that things we thought happened didn't. So firstly, there's been this nice work of coming from supersymmetry breaking, which suggests a plausible alternative for the dynamics. Although in fairness, people always knew that it might be that somehow there's some fermion bilinear that condenses and breaks the global symmetry. But in addition, some arguments that we thought were right turn out to rather annoyingly be wrong. So there's a wonderfully simple paper, again by Eichten and Preskill, now with Pecci and Zeppenfeld, who did a large N analysis of this theory and argued that at large N, you essentially have to have confinement without chiral symmetry breaking. And large N arguments are extraordinarily subtle, and there's a reason why it was Toft and Witten that developed all of these our knowledge of large N, and I think we now believe, at least I believe, that this paper is wrong. There's a work by Bolognesi, Konishi, and Lucio from this year pointing out that this paper is wrong. But I believe the argument of Bolognesi, Konishi, and Lucio is wrong about their argument being wrong. But I think we do have a correct argument. So I think, I certainly believe that the large N limits was known to be confinement without chiral symmetry breaking. I think that's incorrect. I think the correct, it's all to do with actual baryons in large N and how you understand baryons in large N Feynman diagrams, which is subtle. But I believe this is incorrect. There was also a study of discrete anomalies. So the global symmetry of this theory is SUN times U1, and then there's some discrete quotients which mix with the gauge symmetry. And again, Bolognesi and company made a study of this discrete anomalies associated to that, and argued the opposite conclusion to Eichten and Preskel. They argued that you must have chiral symmetry breaking, but I believe these arguments are wrong as well. So all of this is to say that after 40 years, there's a lot we don't understand about these chiral gauge theories. If anything, it tells you how desperate we are to put chiral gauge theories on the lattice, because even the simplest ones at strong coupling, we don't understand. All right, I'm happy to answer any questions about this, but it's more to point out that there's as much confusion in the literature as there is illumination. All right, let me tell you example 2, and this this example and the next one answer Tin's question, which is, are there situations where you just know it works? So example 2 is very similar. Again, I'll start with a bunch of free fermions. Again, with G being SUN. The only difference is now that I've got one fermion in the anti-symmetric representation and n-4 in the anti-fundamental. And for simplicity, it's best if I take n to be even, for a reason that will be clear shortly. What do I do? There's actually various ways I can proceed. Here's the simplest. What I do is I take this H equals SUN-4 symmetry here, and I gauge it. But I don't gauge the full H, I gauge this symplectic subgroup, where this divided by 2 is the reason why I wanted n to be even. All right, if you just gauge it and do nothing else, it turns out that it spontaneously breaks G. However, if you gauge it and add a bunch of extra fields, where the extra fields are scalars plus a gaugino for H, so an adjoint fermion transforming into H, it turns out you can just tune the parameters so that the theory has supersymmetry. This is an SP gauge theory with n equals 1 supersymmetry, and it's among the class of theories that Seiberg and actually a year later Intrigligator and Pulio studied in the 1990s. And now there's no doubt whatsoever what happens. We have control over the strong coupling dynamics in the infrared, and one of the many beautiful phenomena that Seiberg showed can happen in supersymmetric gauge theories is confinement without chiral symmetry breaking, which of course is exactly what we want here. So this turns out to be exactly one of the supersymmetric theories which exhibits confinement without chiral symmetry breaking. It's not any SP gauge theory. You need to tune the number of flavors to be just right, but this is the right number that does it. You know that H becomes strongly coupled, that it binds all of these guys together into basically meson-like pairs. Those meson-like pairs in the infrared include massless fermions. The massless fermions transform into conjugate representation of the guy that was just sitting out the whole story. The upshot is that if you just add some Yukawa terms that couple this singlet to this gauge field, you now know for sure, because of supersymmetry, that when you flow to the infrared, you gauge, you give everything a mass, preserving this symmetry G. As example 3, I'm going to do a version of this, but I'm going to do a version with all the details filled in. And it's a version that's quite nice because example 3 is the standard model. So this is a mechanism to take one generation of the standard model, to couple in some extra fields, but in doing so, give one generation of the standard model a mass, and a mass that can be arbitrarily large. In particular, can be parametrically heavier than the TeV scale. leaving the standard model gauge group, and in particular the electroweak symmetry, completely unscathed. So that's where we're going. All right, so this has some extra ingredients. Before we get going with the standard model, we're going to have to add some extra fermions which are charged under G. None of our previous examples needed that, but this one it turns out does. So take your standard model fermions and add 3 further pairs. The pairs come with conjugate quantum numbers, so there's no problem giving these fermions in red a big mass because they're vector-like. You can see the conjugate quantum numbers have a plus or minus 3 for hypercharge. It's most obvious here. There's a 3 and a 3 bar for the quarks. And one of the pairs is just neutral under everything. They're kind of like right-handed neutrinos, this extra pair. Okay, so there's no problem to start with making these fermions in red very heavy, decoupling them. But as before, the question is, can we now make them light, interact with our previous chiral fermions, and give everything a mass without breaking this symmetry group G? So how do we do it? The point of adding these pairs is that it introduces a new symmetry H into the theory. You see, symmetric mass generation only really happens with strong coupling effects. And the only way to drive strong coupling in 4 dimensions is through non-abelian gauge fields. So you always kind of need to have some extra symmetry H floating around. And if it's not there, as it's not for the standard model, you have to introduce it. So that was really the purpose of these red pairs, was to introduce a symmetry H. The things in the green boxes are doublets under this symmetry group H, which is SU2. So you can see these have the same quantum numbers, these have the same quantum numbers, and these have the same quantum numbers. As before, I should have some, start off with some scalar fields, which Higgs H, make sure the H bosons, gauge bosons have a big mass, and at the same time give masses to these red fermions if I like. But I uncondense that scalar field, make it heavy, throw it away, and I need to understand the dynamics of this H equals SU2 gauge theory. All right, now this is an SU2 gauge theory that's coupled to 6 doublets of Weyl fermions. There's 6 because there's 2 here, and there's 3 here, and there's 1 here. So it's 6 doublets of Weyl fermions in total. Before I think about the standard model gauge group, this SU2 gauge theory had an SU6 flavor, rotating these 6 Weyl fermions. And the gauge group G of the standard model is embedded within this SU6 flavor. So if this is going to fly, I need to find a way to make SU2 confine without breaking this SU6 flavor. And in fact, as it stands, it doesn't work. If you just take SU2 coupled to 6 doublets of Weyl fermions, the SU6 will get broken to an SP3, which as part of that will break the standard model group. So we're going to have to do something else. And that something else means introducing new fields. And the way we introduce new fields is exactly the same as in the previous example. The new fields are just super partners for everything on the screen. That means we introduce a bunch of scalar fields to partner all of these fermions. In addition, we add an extra adjoint fermion, which is neutral under G, but is going to be the gaugino for H equals SU2. So the upshot is when you add these extra fields, you have SU2 coupled to 6 doublets. This is one of the class of theories that Seiberg solved in his original paper on Seiberg duality. And it's rather pretty what happens. So everything in a green box, which I've now given names to, these capital letters you should think of as superfields, but everything in a green box confines. And it confines into, I guess, a meson and a baryon are very similar in SU2, but they get paired together under SU2, everything in a green box with something else in a green box, and they get paired together in an anti-symmetric way. So we start with 6 Weyl fermions, or really 6 chiral multiplets. They bind together to make 15 massless chiral multiplets in the infrared. And it's 15 because there's 6 times 5 divided by 2 is the the anti-symmetry. So what I've written here are the 15 different ways, once you count up all the labels, of pairing together something in one green box with something in other green boxes. And the beautiful fact is that there's also 15 particles that weren't playing a role in any of this. These 15 are the 2 here, plus the 6 here, plus the 1, plus the 3, plus the 3. Everything that's not in a green box. And you can do the calculation and see that the quantum numbers of these composite massless fermions are exactly conjugate to the quantum numbers of the objects that weren't playing a role in the whole game. So what that means is, if I go back to my theory, I had the following superpotential. This is just Yukawa terms. I had this superpotential in the UV. When the SU2 gauge dynamics confines, the first 2 letters in each of these terms binds together to make a new effective field, and these Yukawa-like terms become mass-like terms in the infrared. Again, everything's designed so that the standard model gauge group is unaffected. All of which is to say that there is a way to add new degrees of freedom and give everything in the standard model a mass. Say 1 generation of the standard model a mass without breaking the electroweak symmetry. Of course, it's noticeable this isn't the way nature does it. At least not as far as we can tell. And clearly the Higgs exists, but there is another way in our world for the standard model fermions to get a mass, albeit with the addition of extra degrees of freedom. But it seems presumably not to be something that nature makes use of. All right. Any questions on this?
So I got a bit confused with the energy scales, because there is, first you said we are going to introduce some Higgs fields in order to make these red guys heavy, among other things. And then you were also saying talking about the this SU2 confining. So now, so what is the relation between those 2 scales, confinement scale of SU2 and the mass of the scale of those Higgs fields?
So they're independent. The initial mass you should be able to make arbitrarily large, which I can just by making this Higgs vev arbitrarily large. So now I bring this Higgs vev down, throw the scalars away. The only relevant mass scale is now the strong coupling scale for this H equals SU2.
But you cannot bring it, if you bring it all the way down, then these red fermions are light, so you do not bring it completely down.
As you bring them down, as soon as the Higgs vev drops below the strong coupling scale of the SU2 is kicking in.
Okay.
Yeah, so the original Higgs vev is... sorry, I missed the question, Slava.
Yeah, so I'm saying this answers my question. So the SU2 should confine at a higher scale than this Higgs scale that you also had.
Yeah, so the ultimate masses are the confinement scale of SU2 multiplied by dimensionless Yukawa terms that I didn't include here. So you have 6 different masses that these the fermions in the standard model can have.
I also have a question about this SUSY trick, which seems to be really useful, but you applied it in the second example and the third example, but not in the first example.
That's right.
Where you said it was confusing. So why can't you just always apply this supersymmetrization trick?
I can do it for the first example, actually. You can use an SO supersymmetric theory there. But I wanted to give you sort of all the ways that I know of that this can possibly happen. And the 2 types of theories that I think are known that exhibit confinement without chiral symmetry breaking are supersymmetric theories for sure, and conjecturally certain chiral theories. I think that exhausts the class that's currently known.
Okay.
I'm going to say a few more words about the importance of supersymmetry. Other questions?
Maybe you will talk about that, but I mean, if you break supersymmetry a little bit, do you keep this scenario, or does everything go away?
Yeah, that's exactly where I'm going now, Tim.
Okay.
All right, so I needed supersymmetry. I needed supersymmetry only because it gave me control over the dynamics to do what I want to do. but I'm not addicted to supersymmetry. It's very nice, but it's nice to say things without supersymmetry. So the nice thing here is the answer to Tin's question. If I softly break supersymmetry, nothing changes. Everything still goes along. And the reason is very clear. It's that at the end of the day, I ended up with a gapped phase with a particular symmetry which was preserved. G equals SUN was standard model in the last case was preserved. If I now move away from the UV theory and start to sort of explore the neighborhood, just by continuity, the fermions can't suddenly become massless, but neither can the symmetry suddenly become broken. Because if the symmetry suddenly became broken, there would be Goldstone modes. So there has to be some neighborhood of that supersymmetric point around which this symmetric mass generation or confinement without chiral symmetry breaking has to still survive. So that's nice. So, you don't definitely need supersymmetry. I told you where to head. But if you're somewhere near the supersymmetric theory, symmetric mass generation must still occur. Which leads you to the question, how far can you move from the supersymmetric theory and still get away with it, still have this phenomena happen? In particular, initially, I thought it's not clear the scalars in the supersymmetric theory are really doing anything. And in fact, this is true for a large chunk of the evidence for Seiberg duality in general. So let me just sort of take a slight diversion and talk a little bit about Seiberg duality and what's going on here. So this confinement without chiral symmetry breaking was just one of the many beautiful phenomena that Seiberg discovered. More generally, he discovered Seiberg duality, which is where you take two different UV theories that flow to the same conformal field theory. And in fact, this confinement without chiral symmetry breaking should be thought of as on one edge of that integer parameter class of theories, where one of those theories just becomes a trivial fermion, free fermion, basically. And now there's a bunch of evidence for Seiberg duality. The most compelling is certainly the supersymmetric index, which wasn't around when Seiberg first came up with these. So when Seiberg first came up with these, the real evidence was the dimensions of certain operators which are protected by supersymmetry, the chiral primaries. That clearly relies on supersymmetry. But a big piece of the evidence was the Toft anomaly matching. That these two theories, even though they look very different, have the same Toft anomalies, and these Toft anomalies can be, fifth order polynomials in various things, and they're not straightforward objects. And when they match, when you compute them and they match, you think something fairly miraculous is going on. Now, suppose you just throw away the scalars from the supersymmetric theory. Of course, that doesn't affect the Toft anomaly matching. So you might wonder, is it possible that Seiberg duality or some of these phenomena still occur in the non-supersymmetric theory where you just dump the scalars? The Toft anomalies still match after all, so perhaps you're sort of still in with a hope that that some of this might still hold. And I think the answer is no. And I think the answer is no for interesting reasons to do with the sign problem that come and bite us later. So I'm just going to take a little bit of a diversion and tell you this story about what happens if you throw away the scalars. And as we'll see when we get back to the lattice, this is going to be, I think, quite interesting. All right, so what's the issue? Here's a particular example. So this is the example that I needed to gap the standard model fermions. Consider H equals SU2 with an adjoint fermion and 6 fundamental Weyl fermions. If I add a bunch of fundamental scalars and tune the Yukawas, this is the supersymmetric SU2 theory that confines without breaking the SU6 symmetry, if I add the scalars. But as I've just said, if you throw away the scalars completely, the Toft anomalies of this theory are such that it's very compelling to think that maybe this theory still confines without breaking the SU6, where the Toft anomaly for the SU6, it turns out you can show, is matched by this simple composite fermion. So is it possible that this theory still confines without breaking chiral symmetry? And the answer is no. And the answer is no because of these beautiful results due to Weingarten from the 1980s. These what they're called Weingarten inequalities. I'll tell you briefly on the next slide what they are. They're spectacularly powerful and simple ways to get some information about certain strong coupling gauge theories. So what did Weingarten prove? What Weingarten proved that the proton is heavier than the pion, which you might think we don't need any proof for, because we just have the particle data book and it's sort of obvious because of chiral symmetry breaking. And but he proved the proton is heavier than the pion without any assumption of chiral symmetry breaking. He just showed it had to be true. And the method to prove this is essentially the same as the methods that Waffer and Witten used to prove their various Waffer-Witten theorems, that parity is not spontaneously broken and that theta equals 0 is the minimum of the energy, and so on. In fact, the Weingarten paper came out at exactly the same time as Waffer-Witten. I think they were published within 1 or 2 weeks of each other. They're clearly independent work. Somehow, at least in our community, which means the non-lattice community, Waffer-Witten is very well known, but at least for me, Weingarten wasn't known at all. I think partly because Weingarten's original paper is written in the language of lattice gauge theory. It doesn't need to be. You can reframe the proof almost identically to Waffer-Witten type proofs. But what it relies on, as the Waffer-Witten theorems do as well, is that the theory has a positive definite measure. So the fermions in the theory have to come with a positive definite measure. And the Weingarten inequality is then the statement that there is always a composite scalar that is lighter than the lightest composite fermion. That's the statement here. The proton is heavier than the pion, or the pion is lighter than the proton. If you have a positive definite measure in your theory, a composite scalar is always lighter than a composite fermion. And the way you prove it is simply by writing down the propagator for the composite fermion in an arbitrary gauge field. You then integrate over all gauge fields with a measure that includes the determinant from the fermions. And then you use some triangle-like inequalities to show that the propagator for an object that has 3 fermions is always going to be smaller than the propagator for something that has 2 fermions. That means that the mass of the 2 fermion composite scalar is always lighter than the mass of the, and I think I may have got my inequality the wrong way around, but okay, it's a very straightforward triangle inequality proof that relies on the positive definiteness of the measure. So what does this mean for us? It means that if we want confinement without chiral symmetry breaking, you want a massless composite fermion in the infrared. But the Weingarten inequalities say that if you have a positive definite measure, a massless composite fermion can only arise if there's also a corresponding massless composite boson. But why would a massless composite boson arise? The only reason a massless composite boson would arise is because there's some Goldstone mechanism, because it's a Goldstone boson. But if there's a Goldstone boson, it's game over because you actually broke the global symmetry, the chiral symmetry that you cared about. So the Weingarten inequalities, it's not quite a proof. It's possible you could just get a finely tuned massless boson and a finely tuned composite fermion, but it seems very, very unlikely. So the Weingarten inequalities basically tell you that confinement without chiral symmetry breaking can only happen in theories that do not have a positive definite measure. And the way this appears in the supersymmetric theories is very clear. It's because you have the scalars. So the scalars look so innocuous. They couple through Yukawa terms. But remember, the determinant of a massive Dirac operator is determinant of d/+m and is positive definite only if m is positive. But now you have Yukawa terms, it's d/+phi. And phi is oscillating, positive and negative. So turning on Yukawa terms means you no longer have a positive definite measure and allows this chiral symmetry breaking, this confinement without chiral symmetry breaking to happen. All right, so all of which is to say that if you throw the scalars away in Seiberg duality, the effects that happen in the supersymmetric theory most certainly do not happen without supersymmetry.
So David, a question about the Weingarten thingy. Does the composite scalar and the composite fermion have to have the same quantum numbers or something like that? Or
yeah, there's some relations so that it is a Goldstone boson for the symmetry that the fermion.
Okay, that was the loophole I was going to suggest. But
yeah, let me. Okay, I sketched it. Maybe I should have shown this. So here's the sketch. Except when I was going through this morning, I couldn't remember how all the steps work, which is why I didn't do it. But this is S is the propagator for each fundamental fermion. And so the propagator for chi, the would-be composite, you just write down as the propagator for the three fundamentals, integrated over, this is in the background of a fixed gauge configuration. And then you just integrate over all gauge configurations, and the determinant of the fermion is buried within this measure, which is why you need it to be positive definite. This at large distances is related to the mass of the composite object. And then you have two steps. This second one is the triangle inequality. It's a fancy version of the triangle inequality, but basically it's the triangle inequality. And this middle one, I think, is just rearranging some indices in some way. This object here is a constant, and this object here is the mass of the would-be pion. And you can see that there is some relationship between the quantum numbers that the pion carries and the quantum numbers that this object carries. So that's roughly how it goes.
Okay, thank you.
All right, so that's all I wanted to say about the continuum. And I'm going to briefly say a few words about the lattice, although I'll mostly fail. But the question is now, can we possibly take these continuum ideas and implement them in an Eichten-Preskel-like way on the lattice? This might be a good time to pause for other questions if anyone has any. All good? All right, let me just say a few things about the lattice before I finish. Okay, so the original Eichten-Preskel relied on strong coupling effects on the lattice at the lattice scale, and that seems to have been an obstacle towards realizing it. There are now continuum field theories that do the job of symmetric mass generation. So the question is, can we put those continuum field theories on the lattice in such a way that we can realize this Eichten-Preskel idea and gap the doublers on one side rather than another? So what do we have? We have these two manifestations of the fermion doubling problem, one in momentum space and the other using domain wall fermions in an extra position. Challenge is to try and introduce interactions which only the doublers experience and the original fermions do not. Now, quantum field theory is naturally local in position space, not in momentum space, which makes you think that the obvious thing to do is to try and introduce interactions in this picture, in the domain wall slab. So try and somehow put interactions that the fermions on one side of the slab feel and the fermions on the other side do not. That's the goal. All right. So this is the setup. We've got the fermions we care about here, think standard model, and we've got the mirror fermions here, so the doublers. And we know that there's certain gauge interactions that we can add, which if we can couple it to just one side, will give that one side a mass and leave the other side behind. As I said, the kind of theories we have come in two different classes. One class is supersymmetric theories, although we don't have to fine tune to the supersymmetric point. And the other class is chiral gauge theories, possibly. Now, it's going to be hard to put chiral gauge theory on the lattice because you just sort of run into the same problem again. I have to introduce new chiral fermions for this chiral gauge theory. So the obvious thing to do is to try and somehow put this supersymmetric theory, which importantly is not chiral, and put this supersymmetric theory so that just these fermions here experience it. So that's what we're going to try to do. So we'll work with this standard model setup just to have something specific to talk about. The standard model fermions can be gapped with an SU2 strong coupling gauge dynamics. So this is the obvious thing to do. You introduce an auxiliary gauge field, SU2. The standard model gauge field sits everywhere, but it's just not going to play a role. The whole point is we don't want to break the standard model symmetry. So that'll come in later. But for now, there's this SU2 auxiliary gauge field, which naturally couples to everything. And somehow we want to find a way to make it couple just to one side. So it's a very obvious thing to do. And what I'm going to do here actually is first figure out how this works in the continuum. And then we'll see how it translates onto the lattice. So I think that was a useful way to understand how symmetric mass generation works. So hopefully it might be a useful way to figure out what's going on here. So in the continuum perspective, we just turn on a Higgs field. The Higgs field is such that it's non-zero, it's zero in this region. And then at some point it dips to zero here, which means that you're left with some slab near the right-hand edge where there's an effectively four-dimensional SU2 gauge field propagating. And following some work in the lattice literature by Golterman and company, I'm going to call this the waveguide region. So there's some SU2 gauge field which just propagates along one edge. Now,
can I ask kind of a basic question?
Yeah.
Because if you know how to introduce a gauge field which couples to just one side of the slab, then you are done, because you don't have to do anything. You just introduce the usual chiral gauge field, the one that you wanted, and just.
Oh, you're entirely right, Slava. And of course, it's a simpler way to do it. In that case, you get a standard model and then some decoupled free.
But I thought that precisely that's what people don't know how to do.
That's right. So I think we're going to run into the same problems. Ask me in 15 minutes.
Okay. Let's see your take on this.
We'll see. But we'll see the same obstacles appearing, but I think with a slight different twist. All right. Now what's going to happen? If you do things on the lattice, there's a standard question to ask, which is you should ask, what if there was an anomaly? Because whatever the lattice does, it kind of acts as if there was an anomaly, in a way that I will make clear. So suppose that these chiral fermions here on one edge were in an anomalous representation of H. What would happen? Well, what would happen from the five-dimensional perspective is that you would compute this triangle diagram in the 5D bulk, and you would find that it gives rise to a 5D Chern-Simons term for the gauge field H. And when you introduce the Higgs field in the bulk, the phase of the Higgs field, which of course is usually eaten by the gauge field, fails to decouple in the presence of the Chern-Simons term. And what it gives you is a new light degree of freedom, which propagates on the left-hand side of this waveguide region. That's this dark orange side here. So this omega here is a group-valued field in 4 dimensions, which comes basically from the Chern-Simons term. Can also be thought of as coming from the phase of the Higgs field. When you use the anomaly in 4 dimensions, which relates F wedge F to the derivative of psi, you can show that this theory, this group-valued field that lives on the dark orange region can be thought of as coupling to the fermions in the following way. All right. This term will vanish only if the Chern-Simons term vanishes. And the Chern-Simons term vanishes only if these fermions here sit in a non-anomalous representation of H. Okay. Now, that's the story on in the continuum. All of which means that if the fermions on one edge do sit in a non-anomalous representation of H, one would expect that there's no Chern-Simons term, and one would expect that there's no massless degrees of freedom that live on this dark orange slice on the edge of the waveguide region, if they sit in a non-anomalous representation. And let me just point out that the field theory knows it's sitting in a non-anomalous representation only after doing a one-loop calculation, because that's what tells you what the level of the Chern-Simons term is. All right, that's the continuum perspective. Now let's look at what happens in the domain wall, the lattice perspective. So the lattice perspective is you start with a 5D fermion. That's two, well, it's a 4-component object, so I can think of it as 2 chiral fermions, 2 Weyl fermions in 4 dimensions. For the perspective of, just to try and keep things clear, I'm just going to discretize the 5th dimension and leave the 4th dimension, the 4 dimensions continuous. It just stops me writing lots of stuff on the slide. So here are the 4D kinetic terms. Here are the 5D hopping terms. And the hopping terms, if you tune, it's best to tune the Wilson parameter to be 1. So the hopping terms take this zigzag perspective between the chi's and the psi's. And here are the 5D mass terms. And as shown by David Kaplan and subsequently Shamir, when you solve the Dirac equations in the 5th dimension, you find that there'll be a left-handed 0 mode here. That means, I can't remember if that's chi's or psi's in my notation, but one of them, and the opposite chirality on the right-hand edge, where what that means is that these particular modes of the Dirac equation are exponentially localized close to the edge. All right. Now, what's the problem on the lattice in trying to introduce some waveguide region? You want to introduce gauge fields which live only on one side of this slab. So the orange dots here, or I guess the yellowy orange dots, are where the gauge fields live. And there's no problem at all with gauging them until you come to the interface between the waveguide region and everything else. And at the interface, the hopping term that takes you from this to this is not gauge invariant. And it's not gauge invariant because this transforms under a gauge symmetry, whereas this does not. So in order to write down a lattice action with gauge invariance, you're obliged to introduce a new dynamical field. The new dynamical field sits here. It has to be group valued. I've called it omega. This is work by Golterman and company from the 1990s. And largely, this is the reason why the waveguide region approach fails to work. There's a new light field here, but it's very clear from the construction that why this light field is there. It's precisely the Wess-Zumino term, which was needed in the continuum perspective if the anomalies of the fermions under H did not cancel. Now, the lattice doesn't know anything about the anomalies, so it's kind of just put it there just to, as always in the lattice, to somehow cover its arse in case the anomalies didn't vanish. Same reason the doublers appeared in the first place. But we know, at least from the continuum perspective, why it's there. It's there because it came from this would-be Chern-Simons term. All right, so what now happens? You might hope that when you when you try to do the dynamics of the lattice theory, you might hope that this term becomes massive. This term becomes massive, and it leaves you with the gauge theory that you wanted, coupled to the massless fermions on the end. Now, the Golterman et al. Papers attempted to do the Monte Carlo simulation, and they couldn't do the Monte Carlo simulation in the full theory because there was a sign problem. And so the only thing they could do was a quenched simulation, which you just ignore the fermion determinants. In those quenched simulations, they saw that not only did this Wess-Zumino term, the red guy, not decouple, but there are also essentially massless fermions stuck here and here. So it was almost as if the extra chiral mode that was here had suddenly been transported to the edge of the waveguide region. You just reproduced the whole slab within the waveguide region. However, we know from the anomaly perspective that you shouldn't possibly find that this this mode decouples until you do the one loop diagrams, because the one loop diagrams are precisely how you compute the Chern-Simons term, and you see that whether this mode is there or not. Sadly, it's not going to be possible to do the one loop diagrams, precisely because there's a sign problem for this theory. And in fact, from the continuum analysis or the Weingarten inequalities, you know that you're not going to be able to gap these fermions on one side unless the theory you have here has a sign problem, because theories with a positive definite measure for fermions cannot give this symmetric mass generation that you want. So it's, you know, I've spoken to a few lattice people, and I'm sure they're well aware of the sign problem, but I think this sort of makes it really manifest. It's somehow a chicken and egg situation. There's no possible way to show that this decouples in quench simulations. It just clearly won't. But at the same time, any simulation under which this does get a mass and decouples is necessarily going to have a sign problem. All of which is to say that I'm not sure this Eichten-Preskel way is the way forward. I know, you know, as soon as you solve a fermion doubling problem, the sign problem just hits you in the directly in the face, and there's nothing you can do with it. Let me just leave it there. Okay, I'll finish there, but thank you very much for your attention. Here applause through the window. That's very nice.
Okay. Any questions for David? We actually have plenty of time.
So David, could you repeat once again your last point? So you're saying basically that even if you found to put chiral gauge theories on the lattice, you wouldn't be able to simulate them anyway because of the sign problem. Is this the point?
Yeah, I think that's the point. By the way, there's one caveat which I haven't mentioned. Everything here has been in 4 dimensions. There's a statement in a paper by Eric Poppis, actually, which says that in 1+1 dimensional theories, the sign problem may be absent. Which I don't fully understand. And I can go through the proof, but it doesn't somehow fit with other things I understand about chiral gauge theories, and I don't see what's special in 2 dimensions. But I thought I'd mention it, that there might be a possibility in 1+1 dimensions at making progress. But as far as I can see, in 3+1 dimensions, you're almost obliged to have a sign-like problem if you try and follow this Eichten-Preskel approach.
May I ask a question or make a comment about this supersymmetric theories where we know there is massless composite fermion? So you said something which I want to believe. I also agree that it makes sense that, you know, if I slightly go away from supersymmetric point, that I will still that we will still be in the same phase. But I would like to push back against that a little bit, because there's no gap that we have to overcome, right? I mean, it could be that you simply just, you have a gapless theory with fermions, which are gapless, and then you go into a theory which is gapless Goldstone bosons. And I mean, I don't think that there's... Well,
no, I don't think so. So the strong coupling dynamics confines and leaves you with a massless fermion. But now I take an extra free fermion, and I just couple a mass so that in the infrared there's a mass term for those. So the endpoint of that RG flow is just a gapped symmetric phase. It's got a gap and it's got the symmetry preserved. And now that's completely robust. I can't.
Oh, sorry. Yeah, I'm sorry. I was thinking of just the theory with gapless, but you're putting this 4 Fermi interactions.
That's right. So add that 4 Fermi interaction, and then you're safe.
No, that's sorry. I was just thinking of the theory with massless stuff in the infrared. That I agree with, but you see, you have to get these massless fermions before these 4 Fermi interactions in the UV is irrelevant. But
no,
then,
in the supersymmetric theory, they're actually Yukawa terms rather than 4 Fermi. So they're they're marginally irrelevant, but yeah, they're Yukawas. It's a cubic superpotential.
I guess my worry is that from the UV, as you're flowing from the UV, you need to generate some massless composite before you can generate a mass for them, right? That's kind of the way I think about it.
There are dimensionless Yukawa couplings that sit in front of this, and the masses of the masses that you get is strong coupling scale multiplied by these Yukawa couplings, which should be small. So there's a parametric separation, but I don't know what it means to flow to find a massless particle and then it get a mass. It flows and it gets a mass at Yukawa coupling times strong coupling scale.
Yeah, I think I agree with you in any case. I was more trying to push back a little bit against the argument, but yeah, yes, I think I agree that it should be robust, at least when you put this mass term.
Yeah, the mass term is important. If it was gapless to begin with, it's much less clear. Yeah.
I mean, it's satisfying because I always keep thinking that whatever has the same symmetries and same 't Hooft anomalies, you should get all the phases which are allowed. And if you don't have any 't Hooft anomalies, you should be able to gap everything.
Yes, no, I think that's exactly right. You should be able to gap anything that doesn't have a 't Hooft anomaly, but you might have to work quite hard to do it.
It would be much more exciting if it were actually the other way around.
You mean if there were things with vanishing 't Hooft anomaly that could not be gapped?
Well, imagine that somehow this difficulty about putting chiral gauge theories on the lattice is actually for real. That would be amazing. That would be like a discovery of new physics.
Well,
no, hang on. It would be more amazing than that. And this was, if you take the Nielsen-Ninomiya theorem at face value, it tells us we're not living in the matrix. That we can't possibly be a computer simulation of some alien civilization because no one can simulate the standard model. That's we can't get something that strong from. It would prove Elon Musk wrong, so it's good for something, but it's too strong a conclusion from such a simple theorem.
That's assuming that lattice is the only way to regulate the theory, to put it on the computer, which I don't know whether that's true or not.
That's true.
No, what I meant is that, okay, suppose that just standard model doesn't have a non-perturbative regulator. Well, that means that there is some, perhaps very weak, but some new physics hiding somewhere at some scale. I was just, it's a dream, but I think it's important to rule this out. It's important to show.
How could it not? How could it not? And it's possible that gravity is the only non-perturbative regulator of the standard model. That's feasible, but I don't see how it would point to new physics other than gravity.
No, it just means I was just trying to turn around what Tin said. So he said, we usually believe that everything which is not allowed, everything which is not forbidden is possible. Like, okay, if there is no 't Hooft anomaly, then we have to be able to gap this extra stuff and construct some regulator. But suppose that there is actually an abstraction. I think that's the main motivation. I think that's a motivation also to study this problem that you're studying, that if there is actually an abstraction to non-perturbatively defining the chiral standard model, well, it means that whenever to define the standard model, you just have to have some extra stuff at some scale, which cannot be arbitrarily heavy. That could be one conclusion of this whole study. I mean, very unlikely conclusion, I agree, but it's important to rule this out. So you're saying, how could it not be? yeah, I agree. It seems that it should be, but people are trying and trying and trying, and after decades, nobody is able to do this. And there are people like coming up every now and then with just wrong solutions. Like the most recent one by Koppel and Grabowska, it was back five or 6 years ago. Well, this is discouraging.
No, but maybe we should not be so pessimistic, because the Martin-Lüscher constructions, they achieved already quite a bit. For abelian theories, it works. For non-abelian theories, it works to all orders in perturbation theory. And there is some topological subtle issue that arises when you put the whole theory in a finite volume that was so hard that even Martin-Lüscher couldn't solve it. But it seems to me that it was just some very hard technical problem that maybe needs more attention. I thought the whole development in this direction was extremely promising and partially a real breakthrough.
I agree. Yes.
David, could I ask you a question about this enigmatic equation you had, which was chiral plus vector equals to vector, and then you showed how to get that to work in detail in various cases. Does this mean that there's no real invariant notion of what it means to have a chiral gauge theory if it has no Toft anomaly? Is that correct?
Yeah, absolutely. It's a weakly coupled. In a weakly coupled theory, like the standard model, it has meaning. You can't give a mass.
Right.
But within sort of the class of all possible quantum field theories, and you allow yourself to deform that in some smooth way, the only way to characterize a symmetry is through the Toft anomaly. And if the Toft anomaly is 0, it doesn't tell you whether it's chiral with a vanishing Toft anomaly or if it's vector-like.
But so to push on this more, you started this talk by saying you want to put chiral gauge theories on the lattice. But if there's no completely invariant way to describe this, is there a way to be completely sure you succeeded when you do it?
And I think it's the opposite. It just tells you it should be possible. Here's I think I'm not quite answering your question, Nabil, but I'm dodging it. But here's one what way I've been thinking about it. The kind of theories I've written here are chiral in the UV, but flow to vector-like theories in the IR after confinement or something. And those vector-like theories are then trivially gapped. And there's no distinction between the chiral and vector-like because the anomalies just vanish for the things I care about. It would be very nice to get that to be the other way around, to start with a vector-like theory in the UV and flow to a chiral theory in the IR. And if what I'm saying is true, then there should be no obstacles to that. But then there should be no obstacle towards putting the vector-like theory on the lattice in the first place. So this would be a very nice solution. But I just haven't found any examples that do it. Maybe my lack of imagination, or it doesn't feel like there should be some obstacle towards doing it. But you can see we have to sort of scrabble around and just find some understanding of strongly coupled gauge theories where we can. But that I think would be a beautiful solution, is if vector can flow to chiral.
Right. Then you would really know you succeeded, because at the bottom you would have a free theory that you know where the answer should be, and you can check on the lattice. And then
exactly.
Right.
Yeah.
Okay. No, thank you. That's my question.
I mean, maybe would it be consistent with A theorem and stuff like that?
Why not? You could have a vector-like theory with gazillions of extra fields and.
Right. Yeah, but it's telling you that it has to be something increasingly more complicated, potentially. And which could be the reason why people have failed, because it needs more and more stuff.
This wasn't super easy. Okay, it was easy, but it wasn't totally simplistic. But yeah.
Can you say what's the simplest theory for which, like, this abelian solution by Martin Luescher, does it work in any D or just in 4D? I know the paper, but I never studied it.
It for sure works in 4D, and I'm sure you can. I'm sure you can do it in 2D, but it also involves a lot of topological analysis, which might become more complicated in higher even dimensions. But with a U1, I could imagine that you can do it in any dimension, any even dimension.
But by the way, in 2D, it's also simple to do for abelian, but not for non-abelian. But using a very different method. So in this is roughly what Wang and Wen do in their papers, although they don't use this language. But in 2D, ultimately we're going to turn on multi-fermion terms, which are going to gap the system. Again, sort of Eichten-Preskel, like gap one side of the domain wall. Those multi-fermion terms look as if they're irrelevant, but 2D free fermions have a large moduli space. And so you can turn on marginal parameters that move you in that moduli space and take you to a point where those multi-fermion terms actually become relevant and then just gap preserving a chiral symmetry. So 2D abelian theories are, for dynamical reasons, no topology is needed, for dynamical reasons rather straightforward. For non-abelian, there's no such mechanism.
You mentioned the work of Simon Cattrall, and also Shailesh Chandrasekaran has worked on these things. This symmetric mass generation mechanism. And if I remember correctly, he started out in 3D and then moved to 4D. And in 3D, he found a second order phase transition, whereas in 4D, there was some intermediate phase, which I forgot what exactly it was, but there was something that didn't seem to work so smoothly in 4D as in 3D. I'm just saying what I remember about it, and I'm wondering whether you have thought about this.
I actually had in mind some subsequent papers by Simon. I can't remember the setup of those earlier works. That they were interesting, and I read them, and I'm afraid I don't remember which symmetries were there. So Simon's more recent work has been with looking at staggered fermions.
Yeah.
And there's some exact anomaly on the lattice for staggered fermions, although weirdly not an anomaly that has a continuum analog. It's related to the gravitational anomaly, but it's not. It's Euler, not Pontryagin, something like this. So sorry, the details are escaping me.
Yeah, so maybe it may be irrelevant at the end, but maybe you want to look up what Shailesh Chandrasekaran did. He wrote papers in 2016 or so about these things.
Yeah, I did read these papers some last year.
Yeah. I think the result was not totally encouraging at the end in 4D.
4D.
Okay. Any final questions, thoughts?
Yeah, maybe another remark. You make these interesting connections with the sign problem. And of course, I mean, chiral fermions, they produce some complex phases in the fermionic measure and the fermion determinant. So I think it's very likely that if you want to simulate them on a computer, you will face sign problems. But the sign problem per se is not really a feature of a theory, because you can imagine setting up the path integral in a basis where the sign problem would disappear. If you are infinitely clever, you simply diagonalize the Hamiltonian and work in the eigenbasis of the Hamiltonian. Then every sign problem is solvable by an exponentially hard procedure. So this basis dependence of the sign problem makes a statement that you made not entirely clear to me. So if you're in a basis of gauge fields as we usually treat them in lattice field theory and the coherent state basis for Grassmann fields as we usually do, then I guess this is what you really say, but it's not excluded that some more clever reformulation of the path integral might actually get rid of the sign problem eventually.
No, I empathize completely. An extreme version is holography, where you can take these theories with fermions and put them at chemical potential and solve them exactly. It's just some Reisner-Nordstrom black hole in the bulk. But it's a clever change of basis.
Okay. So let's thank David again for a great talk.
Thank you all.
Thank you, David. And I'll see you now.